Alright, welcome to module 4.1. In this module, which will be a relatively short module, we'll look at how to expand on shear and moment diagrams to draw deflected shapes of beams and frames. The objectives for this module are to first explain the fundamental relationships between moments and deflections. Secondly, we'll describe some of the basic assumptions that we make when drawing deflected shapes. We'll practice drawing some deflected shapes, and then we'll look specifically at how to use moment diagrams to help in drawing these deflected shapes. So let's start by looking at the fundamental relationship between shear, moment, angle, which we label as theta, and deflection, which we label as y. Now here we have an example of a loaded, simply supported beam. If you recall from the last module, the relationship between the load and the shear was simply a differential relationship where the derivative of S, the shear, is equal to the distributed load. Note that in this particular example the distributed load is 0, so the shear is simply a flat line. The moment is just one derivative up from that, so we have the relationship that the derivative of the moment with respect to x is equal to the shear. So in this case we have the moment diagram as a linear function. The angle at which the structure reflects is simply one derivative up from that. The angle at which the structure deflects is simply one derivative up from that. Except that in this case we must also account for the material and geometric properties of the structure. So we get, now we're dividing the moment by Young's modulus and the area moment of inertia. But the overall result is that the angle is, in this case, a quadratic function. And finally, as long as we assume small deflections and small angles, the angle is the slope of the deflection. The result here then is that the deflection forms a cubic function. Note that in most cases we'll simply skip the angle calculation and go from moment directly to deflection. So usually we use the following relationship, where the second derivative of the deflection is equal to the moment over EI. Now it is possible to solve for the deflection using the moment diagram and this relationship directly. That is what's called the double integration method. And it's explained in detail along with the derivation of these relationships in section 7.2 in the book. However, in this class we won't go very deeply into this method. Instead, we'll take a more qualitative approach to drawing deflected shapes. But it is important that you understand fundamentally what the relationships are between shear, moment, angle, and deflection. So for the rest of the lesson, we'll look at techniques for drawing qualitative deflected shapes. A qualitative deflected shape is simply an approximation of the deflection, or also referred to as the elastic curve. Now, why is it important to learn how to draw qualitative deflected shapes? Well, there's two main reasons. The first is that it allows you to do qualitative calculations. This could include, for example, identifying points of maximum deflection. This in particular is important because later we'll look at other techniques for calculating deflection precisely, but they'll only work at certain points. So if you can tell ahead of time where the maximum deflection will be, that will facilitate analysis tremendously. Another sort of qualitative calculation might be comparing the overall effects of different loading patterns. The second main reason is simply to gain physical insight into the structural behavior. This can help you to anticipate failure modes and also to double check the results from your calculations. Alright, so let's look at the assumptions we make when drawing deflected shapes at supports. For a roller, we know that motion is constrained only in the y direction. So we know that deflections in the y direction must be equal to 0. In other words, there is no deflection in that direction. However, it is not constrained to move left and right in the x direction. So generally we can say that changes in the x direction are non-zero. It is also not constrained against rotation, so the angle is also non-zero. So in general, when drawing a roller, you are allowed to move it left and right, and the beam is also allowed to rotate around that support. Note that we always draw the angle from the horizontal, and the deflected shape is really representative of the center line of the beam. So always draw the rotation around the center line as well. Now the pin connection is restrained from motion both in x and y. So we have both change in y and change in x equal to 0, but is not constrained against rotation, so our angle remains non-zero. Therefore, my beam is allowed to rotate around the pin support. Finally, my fixed connection is restrained from all three types of motion. Therefore, my beam must always come out at a right angle from a fixed support. When it is sufficiently far from the support, then it can start to deflect, like so. Connections follow a fairly similar pattern. When we have rigid connections, as you see at the top, that angle must remain a right angle. Be sure to always label that in your figures. But in this case, the joint is allowed to rotate in general as long as that angle remains 90 degrees. So in general, we can have something like this. Note that my connection has rotated clockwise and the beams have deflected, but at that joint, at that connection, they still remain at a right angle. A pin connection doesn't have that constraint, so it is able to rotate, and the beams are able to rotate relative to each other as well. So you could have a configuration like this, where the angle is greater than 90 degrees. You could also have a configuration where the angle is less than 90 degrees. In this case, you don't have to label the number of the angle, just simply have to make it clear that it is not 90 degrees. So usually for rigid connections, we explicitly state that that's a right angle. For pin connections, we leave that unlabeled. All right, so let's look at a couple of simple load conditions in structural systems. Here we'll just use plain intuition to draw these deflected shapes. Then for more complicated cases, we'll actually use the moment diagram to help us. So in the top left, we have a cantilevered beam with a distributed load. So we'll start at the left side. We know that it's a fixed support condition, so we know that the beam must come out at a right angle. Then the load is in the downward direction, so that's going to induce a negative curvature in the beam, and so it will deflect down like so. Obviously, for most structural beams, these deflections will be relatively small, almost imperceptible, but we of course exaggerate them to make them more obvious. Okay, now let's move to the top right, where we have a simply supported beam with an overhang, and it's being loaded in between the supports. So in this case, because of the downward load again, this will induce a negative curvature. But this time the supports are allowed to rotate, so we have something like this, where we have an angle there, as well as an angle here. Now the overhang actually isn't loaded, so it will simply project straight out like this. Now let's look at a few simple frame examples. On the bottom left, we have a pinned and fixed frame. This is in fact an indeterminate system. We won't see too many of these quite yet, but we can still use intuition to draw the deflected shape. So I'm going to start at the top. I know the load is coming from left to right, so I expect the top of the frame to move to the right. So these joints are going to move to the right, and then simply I need to connect the supports to these joints. So at the left side I have a pin which is allowed to rotate, so I can have some sort of angle there. Because it is coming in general at an angle here, but this has to remain 90 degrees, then I may get some deflection here. Typically it will look like this, sort of like an S shape, and this also has to be 90 degrees here, and it has to be 90 degrees here at the bottom as well. So simply I just need to connect these two in that way. So again, keep in mind these are not exact, but they approximate the behavior of the frame. Okay, let's look lastly at a pinned frame with two fixed supports. Okay, this is being loaded in the other way. So again, I start by looking at the joints at the top. I know that they'll be moving to the left in this case. And simply I just try to join them up. So the beams leaving the supports must be at right angles, and then they join at the top. Very similar case for both. And in this case, because the top beam is allowed to rotate, it really does not have a lot of constraints to it, and so it'll remain fairly straight here. So notice I have one angle is less than 90, one is greater than 90. Alright, so that's a general intuitive approach to drawing deflected shapes. It works very well for relatively simple loading conditions like these, where we have essentially one load acting on the structure. When we have multiple loads, it's much harder to anticipate the behavior, so it's better to use the moment diagrams to guide you. So let's look at the example from 3.2. If we recall, in that lesson, we calculated the moment diagram for this beam, and it looked something like this. So we went from positive curvature on the left side to negative curvature on the right side, going through this point here, which we typically call an inflection point. This is a change in curvature. It's also a point where the moment equals 0. Okay, so we need to be conscious of these points because they'll impact the shape of our deflection diagram. So we know that for the left side, the curvature is positive, so the deflected shape is going to be concave up. And it's allowed to rotate at A, so I can have an angle leaving that point, like so. Now, once we cross the inflection point, the curvature needs to change, so that beam needs to frown or be concave down. So that will happen because there's not a lot of space, will happen relatively slightly like so. So in this case, just to be clear, we'll put concave up here and concave down. Note that we also have an angle at B there. Now let's look at a slightly trickier example. Here we have a pin-connected beam that is fixed at one end and roller supported at the other end. Just to practice calculating reactions for these beams, we'll actually go through that process fairly quickly. So what we need to do first is split this beam at the hinge in order to solve for the reactions appropriately. So we'll draw two free body diagrams. Again, I'm careful here to draw the forces equal and opposite for the hinge that we just separated. All right, and I'll start on the right side with the sum of moments around C. From that equation, it should be fairly easy to see that dy is equal to 2p. Similarly, I'll use forces in the y and forces in the x to calculate cy and cx. These are fairly straightforward calculations, so I'm just getting straight to the point. Alright, now we have cx and cy, so we can jump over to the other side. I'll start with forces in the y and forces in the x. That gives me that both ay and ax are 0. And so that leaves me to calculate the moment, which I do with sum of moments around C. And that gives me the moment is equal to P times A. Okay, so we have the reactions. Let's go ahead and calculate shear moments and then estimate the deflection. So we'll start with the shear diagram. There is 0 reaction in the y direction at A, so we start there. And there is no distributed load, so we know that's going to be 0 until we reach point B. Then we're going to have a jump down of P. Then it stays constant until we reach C. Now note that the forces at C are purely internal, so they don't affect the shear diagram at all. This continues constant until we reach the next external point load, which is 2P. So we jump up to positive P, and then we stay constant until E, where we have another jump down to 0. Now the area here is negative 2P times A, and over here it's P times A, positive. So we're going to draw the moment diagram next. We have a clockwise moment that is a jump up to PA, then no shear, so that's constant. Then we go down by 2PA with a slope of negative P. That takes us to negative PA on this side, making sure to draw the moment through 0 there at C. And then the moment increases with a slope of P all the way to 0. Alright, so now we just have to label the curvature. It's positive on the left side, negative on the right side, and then we start to draw. So let's look at the supports first. We know that the roller at D doesn't experience any lateral forces, so it should stay put at that point. Obviously it cannot move up or down as well, so we know that the deflection diagram must go through that point. We also know that the beam must leave the left side at a right angle because it is fixed. So the only way to maintain positive curvature by leaving at a right angle here is to curve up, like so. It's just not possible for a cantilever beam to have a positive curvature and curve down. So that might be counterintuitive based on what you're seeing because it's being loaded down, but that is what the moment diagram is telling us. Once we reach the inflection point at C, because it is a hinge joint, it is allowed to have sort of a non-continuous transition in curvature. So we make that clear. And from then on, it has a negative curvature. So we draw something along these lines, making sure to pass through 0 on point D. And there you have it, your final qualitative deflected shape. Now I encourage you guys to model this, for example, in Mastan and look at the exact deflected shape. It's not going to be exactly like this. It'll have a little bit more nuance to it, but this is the general gist. And we can tell that the maximum deflections will either happen at C or will happen at E. And that's what we're really after with these diagrams. Now let's look at some frame examples. This first example is taken from Module 3.2. I've already given you the moment diagrams here. We're just going to go ahead and note the curvature as well here. Always a good idea to do that. And now to start drawing the deflected shape, I'm going to focus first on the supports, particularly support B. So because it is a roller, it can move left and right, and we do see that there is that 20 kilonewton force pushing the frame to the right, so I can expect this to shift right somewhat. By extension, I don't expect any compression of the frame, so I know that point C is also going to move to the right. Okay, so now I have basically my joints drawn out so I can start connecting them using the appropriate curvature. The load on the top beam CB is essentially downward. We have constant positive curvature for the whole beam, so it's fairly easy to draw like so. Next, I just have to join points A and point C, keeping in mind the positive curvature here. And I also have to be conscious that the angle at C must be right. So that doesn't look particularly good, so I'm going to adjust the way I drew the shape of CB to make that look a little better. And finally, I just make explicit where I have angles. There's an angle there at A, and there's also an angle there at B. Let's look at a second frame example. Here we have a hinged frame supported by 2 pins with a lateral load applied. Now the best thing to do is, of course, to split this frame into sections and solve each section as an independent free body diagram. Note that the way I've broken it out here, I've chosen to apply that load at point D for the beam DB. You could also choose to apply it to beam CD, like so. Either way, you're going to get the same overall result. So just simply pick something that makes the solution easier for you. So solving the free body diagrams using the configuration on the left, we get the following result. And notice that the forces here cancel out, so that's effectively 0 horizontal force there. So let's go ahead and draw the shear moment diagrams for this, keeping that in mind. I'll start at the left with AC. So we have a positive jump of P, and then constant, and then a downward jump of P. So this is positive shear. Then we have a downward jump of P at C, constant, and an upward jump. So this is negative shear here. And like I mentioned, at D, we have essentially 0 horizontal force at both ends. So this is simply a 0 shear beam. Let's go ahead and label the areas as well. So the areas will be equal to P times A in both cases. And so that leads to fairly simple moment diagrams as well. Again, starting at the left, I'm going to start at A. My moment there has to be 0 because it's a pin support. And then I have a positive slope of PA over a distance of A. I get the following diagram, and similarly at CD, I get the following. Note that again, the moment at the hinge must be 0, and my clockwise moment, PA at C, gives me a positive jump in moment. Finally, my beam DB has 0 shear, and it also must be 0 moment at both ends because I have a hinge and a pin support. So the only possibility is that is a 0 moment beam as well. Okay, so that makes for an interesting deflected shape. I'm going to start again looking at the movement of the top of the frame first. The load is acting to the right, so I know that C and D are going to shift to the right. So now I'm going to join B with D, and in this case I know this must be linear because the curvature or the moment, either one, is 0, so it's got to be a straight line. There's 0 curvature to that member. I know my curvature from C to D must be positive, smiling up, so I draw something roughly like that. If I want it to be as correct as possible, I can make my curvature slightly larger on the side of C, simply because the moment is larger on that side, but that's not critical. And then again, I join A with C, but I have to make sure that because that is a rigid connection there, that is a right angle. So now I can connect point A to point C, making sure that my curvature is in fact positive. So that's where it can get a little tricky, and you may have to make some adjustments to your deflected shape to make that work out. So overall, we have an angle here at A. We have an angle here at B. Alright, so in summary, we've learned how to draw qualitative deflected shapes and develop an intuition into structural behavior. And we've seen how by simply predicting the direction of deflection, rotation, keeping in mind the constraints of the structure, we can draw some pretty accurate deflected shapes without having to do numerical calculations, which is useful for understanding where the maximum deflections might be and so on.